starting from an input image, so you have the mask, what you have in there. You want to generate different sequences of the same type of facial expression here, the smiles. Right? So on one hand, we want to have, of course, all the sequences to be all smiles. On the other hand, we want to have these smiles to be as diverse as possible. Right? So that's why we have what we call a push-pull loss. On one hand, we want to have them as diverse as possible, but we want to keep them together to be within the same class category. Okay? So why is this useful? And this is what we also show in our paper, is that you could, for example, do some data augmentation. So if you want to train, for example, a facial expression system for video sequences, getting a lot of data, it's very expensive. But in this way, if you have diversity of the data, you could generate a lot of sequences, practically an infinite amount of sequences that can be used for training. And then we show that this is also going very well having this type of information. And also, at the end, you also want to make sure that you are preserving the identity. So the same person, it's the one that is doing the smiling. You see here, you can have in the B part, you have one sequence, and then you have we have an input image. You can generate different type of smiles, but they are different in the sense that the intensity is different. In some cases, the eyes are closed or the eyes are open. The mouth is wide open, or it's only kind of a smile, and so on. So here what we have the system in which we go first through a conditional recurrence landmark generator. Then from here we go into this multi-mode recurrent landmark generator module. So we are practically generating sequences of landmarks, how they are changing. And then this one together with the input image are used to do some texture mapping, and we are generating the sequences of the neutral image and the label that we obtain. Yeah, so we first encode the landmark image and generate sequences of landmarks according to the conditional label. In this case, will be smile or whatever expression you want to do. You want to generate k different landmark embedding sequences, and then to translate each of the sequences into a face video. Well, some details. So this is an AMRAP model. Again, here we use an LSTM, very simple type of things. And this LSTM is used as a recurrent unit to, which is receiving the input, the concatenation of the previous stage and the embedding of the conditional label. Here we have what we call the push-pull loss. On one hand, we have an MSE regularizer to keep the sequences together, and we have a softmax in order to obtain to make sure that the sequences are diverse. And we use then two levels of LSTM with generating different styles and generating the conditional sequence. And finally, we are using this landmark-guided diverse smile generation, in which we are using the skip connection to preserve the identity. So here, it's an image-to-image translation. We have the input image. We have the generated sequences of landmarks. And then we generate the image according to the deformation of the landmarks. Now, what you can see here, different sequences. Maybe it's hard to tell because the image is very small, but you can see that, for example, the output stuff here, the mouse, it's open here, it's closed, and so on. Right, so you can just generate a lot of differences into here. Let me play the video so you see. Between we have what we call spontaneous smile and pose smiles. In some cases, they are exaggerating smiles. In some cases, some kind of small smiles, and you can generate different sequences according to what. In some cases, you have wide open mouth. In some cases, it's closed mouth, and so on. Right, so you could do this kind of way. You can generate practically an infinite amount of sequences that are as diverse as possible, and they can be used very well for training your classifiers. And the competitors, as you see, they have a lot of artifacts. In our case, it's very smooth. For example, VideoGun will produce a lot of hallucinating type of information in there. Okay, so here, the only goal here was to obtain diversity. Then the next step that we wanted to do is now to do image animation. And what I presented in the previous hour, practically what you can do, you can always, of course, generate different frames. But the problem is that you want to make sure that these frames are coherent in the temporal domain, right? So just modeling the appearance part is not sufficient. What we want to do this also the unsupervised motion transfer. So here what we do practically here, it is what we call the monkey net. It's an image animation with moving key points. So we have, again, the encoder-decoder type of architecture. We have this key point detector. And practically what we are modeling, we are extracting these key points that will be specific for a particular motion. And we are looking at what is the deformation of these key points, so then you go from the source to the target. And of course, we have alignment problem. So here, what we do, we are obtaining this motion-specific key point detector. We have a prediction network and an image generator. We'll give you some details in the next slides. And this generator reconstructs the image from the key point position and the differences between the different part of the different key points. And we are using optical flow to handle the misalignment between the two generated spaces. All right, so practically the motion prediction, you are just having the appearance of the first frame, the key point motion, and the motion predictions, and then we just predict the mask. We tell on which part of the image we need to change these key points, and we get the residual motion. And then at the testing time, practically we generate the video with the object appearance of the source image, but with the motion from the driving video. Yeah, so that was the example that I was showing you with animation at the beginning of the presentation. So some example here. Let me play it with the video. Yeah, so these are some of the key points that we extracted. You see, in some of the cases, the key points are related to, let's say, some geometrical parts of the face, but not always. And so this is unsupervised, so we are not explicitly telling which key points to extract, but are the key points that are the most representative for the motion of the video that we obtain. And you see it's working. We have no assumption about the object we want to animate. So not only faces, but could also be bodies, could also be a robotic arm, for example. Yeah, and then what you can do, you can just get a driving video, and you can just take the person and whatever motion you want to do in there. And it's working quite reasonable. This is a little bit more complex. It's a Tai Chi data set. So it starts with, so we have an input, the top row, and then you have the driving video, and you are just generating the motion of the guys that do exactly the same stuff as the driving video. You can also do it with, with some kind of animated characters and so on. It doesn't matter. In the previous one, you notice that there was some problem with the background. In some cases, it's having some trouble with filling up the background. I'll tell you how we did it in the another slide. And here, you can just do what I showed you before. You have a driving video, I don't know, Obama and Trump saying something, and then you can just animate the other images to do the same motion. Here, the code is available. It's called the first order motion model. We call it the first order because we look only at the derivatives, but the first order derivative. But if you want to do it a little bit more complex, you can also do it in using the second order and so on. And of course, as any other applications, you need to get some sort of evaluation, and our results are always, it are better than the previous one. Another thing that we obtain here is the fact that when you do a user study, the proportion of time our approach is preferred to, the state of the art, it's much larger. So in our case, it's about 80% or more. So, as I said, the code is available. This is, it's a short video. I'm not going to play it all. It's that there is one guy who is kind of doing some technology scouting. He's doing this kind of 2 minutes video paper, and he took our code and he tested independently. And then it's kind of, he created this video. I can let it play at the beginning. So this is our paper. It's an EURIPS paper. And so kind of he took it independently. He was running all this stuff and he was doing the animation.
It is important for you to know that everybody can make deepfakes now. You can turn your head around. Mouth movements are looking great. and eye movements are also translated into the target footage. And of course, as we always say, 2 more papers down the line and it will be even better and cheaper than this.
And any kind of talking about the technology and so on, the one that I already said. I don't know if I can skip some of the stuff.
See me doing it here. And again, you see this technique in action here to demonstrate that it works really well for video footage in the wild. Note that these talks and consultations all happen free of charge, and if they keep inviting me, I'll keep showing up to help with this
So
in
we
the
had nothing
future
to do with
as a
this video,
service to
he
the
created
public.
it independently.
The cool thing is that later, over dinner, they tend to come back to me with a summary of their understanding of the situation, and I highly appreciate the fact that they are open to what we, scientists, have to say. And now, please enjoy the promised footage.
Dear fellow scholars, this is 2-minute papers with Dr. Károly Zsolnai Fehér. It is important for you to know that everybody can make deepfakes now. You can turn your head around, mouth movements are looking great, and eye movements are also translated into the target footage. And of course, as we always say,
whatever, so you can just take your own
the
characters and you can work on it. The good thing about it, again, we didn't put anything into the model that you have to move the eyes or you have to move the head and so on. So it's just a model in an unsupervised way, just learn that these are the important motions that would represent what you want to do, and then you can just do it by itself. And another powerful thing is that we had no assumption about the type of object we have in here. So okay, with face it's easy, but then when we do bodies and so on, it's a little bit more complex. And I forgot to tell you, so this all started, it was more like a joke of mine telling my students that, well, why don't you just generate me doing the moonwalk? And this is exactly what they started to do, right? So it just taken an image of a body, you just get a video of, I don't know, Michael Jackson doing the moonwalk, and then you can generate me doing the moonwalk.
You have the video?
I don't, but it would have been good, yes. Another thing that we started to go with that, so here, practically, we had an entire driving video, and you just generate, to do exactly, to copy the motion from there. But the idea was that why can't you just now try to generate only part of the video, or try just copy only part of the video? And this is, the next extension was to use this motion supervised copart segmentation. So the idea is to leverage the motion info to train a segmentation network without the annotation, right? So you can use frame pairs as the training, so source and target, to predict the segment in the target that can be combined with the motion representation between the two frames to reconcile the target image. And then as the inference, you use a trained segmentation model to predict the object part segments, right? So you can just take it and you are just predicting what are the segments that are going to be animated in some way. And here we have several things, something like, so we have this sub-supervised copart segmentation. The segmentation model will predict the segmentation map between the source and the target, and the affine motion parameters. And then the reconstruction model will compute the background visibility mask, right? So we need to know exactly which part of the things we need to animate. It's in the motion, so the optical flow. And then we are reconstructing the target by warping the features of the source frame and masking the occluded frames. And you can obtain something like this. So here, practically what we do some part swapping. You have a mask, so the one that you see it in there is more like an attention map. And you can just replace, now you have the source, you have an image, you have the target, particular video, and practically here, with a mask, we are just extracting some particular features from the stored image, and we just paste it on top of the video. See, so you can get the nose from Michelle Obama, or you can get the lips, and you put it on top of the target video, and so on. I mean, we can put glasses, beard, whatever you want to put into there. And it's all coming practically for free from this segmentation map. Right, so here you take the hair, for example, or the beard area, and you can just put it on top of your target video. Of course, there are always problems with, ethical things. How can you do this type of, deep fakes and so on? Well, I mean, we just show that we can do it, and how this can be, counter-attacked. Well, since we know how to do these fake videos, we should also know how to tell that it's a fake video. So that's our idea. It's kind of reasonable. If I will give you the video without telling you if it's fake or not, I think it will be very hard to tell if it's really fake. So So this is again the Tai Chi data set in which we were exchanging some of, let's say you see the shirt, for example, or the trousers of the guy. There is a little bit of problem with the background stuff. There is a little bit of leakage of the guy. You see you have the blue stuff behind. Okay, well, we were going even further. So this is a paper that was presented at EGCE, well, a few months ago. So here we were combining, we were doing these generative nerves together with a texture generator, and then you can generate several things. You can change the camera pose. You can change the texture of generated images. You can do some translation of the model, or you can also do the semantics of the image. For example, you can go for short sleeves to long sleeves and so on. So you can just doing it without additional 3D information. You are still able to learn a 3D human representation with a photorealistic controllable generation. I don't tell you details, but you can do this type of things. And then just another thing that you can also do, you can try to do this face swapping. So this is, well, you probably don't know, but Vasco Rossi is probably one of the most famous Italian singers, at least in Italy, is very popular. And I generated this video, and well, can you tell me if it's fake or it's real? Well, so the video is real, but then the face is real or is fake? Can you tell if it's a mask or not? Well, let me help you. So practically what I did, it was, I created this video from, well, it's my good friend Alberto Del Bimbo. He just retired a few months ago. And practically what I did, this is the original video. So this is the face of Vasco Rossi. I just took the face of Alberto. I put it on top of the head of Vasco Rossi. And then, well, I have the videos. It looks quite good, actually. Well, I chose this video. Io sono ancora qua means I'm still here, right? So the fact that he's retiring, but he will still stay there, right? So he liked it quite a lot. I mean, it was more like, so again, you can do this kind of seamless generation of videos, right, with your face or without. I mean, I just realized how similar Alberto is to Vasco Rossi. You know, in general, you will not realize it, but if you put it together, and you look at the image, I use those images as a source image, you know, to crop the face. And it's working quite well. So you can play around with this type of things, right? So that's why, so the next step, so I'm showing you some kind of, you know, an historical walk through the things that we did into this area. So now we go towards playable video generation in environments. And there are a few papers in the group that we work on this. So the idea is that you want to realize the user intent. Yeah, so you can have the user control, for example. So this is what we had so far. You had some, you know, a TED talk, somebody saying something, and then, you know, generating the video of the same person. Or you can also use some text control, and you generate the video based on what you obtain there in the text control. But then you want to go even further. So you want to entertain the user, for example. So you want to kind of generate some video games in which the user is playing with the game logic and have some control about what's going on in there. But this is a Super Mario type of thing. It's very easy. But then you can also go to something like, so of course, it's a dynamic environment. You have different agents in the game, and you have an objective to reach. But then in real life, you have this type of game. Okay, so what you would want to do now is to give the user the power to have this guy, whatever the guy is. I think this is Murray probably here. Or no, this is Wawrinka. So you can take the user and you just move Wawrinka around, but it's still him, and still be realistic, right? And just play the videos. For example, if you go to the right, since he's a right-hand guy, he will have to kind of move the hand like this. You know, if you go to the left, he will have to do the backhand, and so on. Also, when he goes to the net, he will have to go with a racket to be high. So these kind of things you would want to put into your model, right? So this is what we are playing with these, you know, playable models in which you have user entertainment plus learning, and have the user control as well. Okay, so it's very simple. You have a set of unlabeled videos, so you need to understand the logic of the game, right? So you need to understand what it means to play tennis. Then you have this generative and dynamic model, and you can also play the user in which you can stay him. Well, you move to the right, you stay, you move forward, and so on. So you have this kind of stages in which, of course, the user will have to be animated. Right? And then how you do this, you have two different streams. So you have at moment t and moment t+1. You have different stages. You have encoder decoder type of things. And then in between, you have to put a dynamic network and an action network that are working together. Right? So you want to, on one hand, to model the temporal part. On the other hand, you want to model the actions that are in there. Okay, so practically this is, I showed it. So you want to have, for example, you start with training, you have a set of unlabeled video in which you have the videos depicting an agent in an environment. And what we assume here is that we have no annotation at all. So we don't annotate the videos at all. And then you want to allow the user to input action to the model through a controller at the test time. And at the end, what you want to do, you obtain something like this in which you can play around with the same guy. Yeah, so here a little bit of details. So first of all, we sample the input sequence and use this encoder network to extract the frames. Then we use pairs of successive features to infer the action that was performed by the agent using this action network. We'll give you details in the next slides. And then given the frame feature and the action, you are just training this recurrent model to produce feature represented as successive states. Okay? And then this successive state is translated back into the image using a decoder network. And you could stop here, but then in order to obtain a little bit better results, what you can do, you can just loop it back. You have encode back the produced frame using the encoder and the action network. And you are using this kind of different losses, so the self-supervision loss on the frame features, and the produced actions. Right? So we use this mutual information maximization loss between actions and the reconstruction actions as a drive mainly loss for the action learning. And then in the end, you unwrap the model and keep on going like this forever. And then in the action network, practically what we have these embeddings. And we look at the differences between these embeddings, and this will tell you what is the action direction. And when you visualize it in the TNS plot, you can see the representation of the different type of transition that are observed in the training video, right? So you cannot, of course, there are some limitations. From one stage, you cannot just run to any other stage because, of course, it's a continuous game. So if I am at the net, I cannot just be in the next stage, in the baseline. So I will have to go through some intermediate results. So this is what it does. And then we have this NLP to tell you, for example, which action is done. So if you move left, right, up and down and whatever. But also, you can also do it to understand how the action is done. So you can understand the speed and the limb movement. Yeah, so these are some examples that we, in an unsupervised way, we extracted from the video. As you see, so the player moving left, right, going towards the net, going in diagonal, and so on. So these are the 7 actions that we learned from tennis play. You can also do it the same with, let's say, this is a robotic arm. You can move things, up and down and whatever the robot can move. And you can also do interpolation. So, of course, the game, it's something more complex. And then practically what you do, you can just interpolate between different actions, and you can just generate, the video in that particular things. So let's see how it works. You see the user, it's using, in this case, a keyword, and is moving the guy. It's telling you also in which action you are still there. You see that it's generating is quite natural in the sense that the legs are moving naturally, and also the pose is correct. Of course, we don't have the ball and we don't have the racket. So, well, the student is working at it right now. We are submitting something to SIGGRAPH. Well, I think the deadline is very soon. But more or less, as you see there, the position of the player in the game and the pose according to the right location, it's quite natural. And this is one of the first attempts to kind of go towards this kind of playable environment, right, in which you show things that look like in a natural way. And then, well, you can start playing around it, so you can play around with this, forward, upward, and so on, and it's looking quite reasonable at the motion. But then, of course, you want to go, so here we have like the single state controls type of things. But what we want to do, we want to go even further, and that was a paper at CVPR last year, in which we were looking at not only of position of an object, but we have the pose of the object, the style of the object, cameras, and so on. So practically here, what we want to do, we want to learn a model that represents the observed environment, and you can control the players, control the style of the field, you can also control the camera. Of course, with some limitation, and the one I will tell you what's going on in there. Right, so we have the same type of things in which you have different frames, you have the encoding, you have the section models, and the synthesis model. There you can also change the cameras, and you can also change the styles. Right, so the difference is here, it's very similar to what we had before. You have the encoder-decoder, and then you have this dynamic network, the dynamic and the action network. On top of that, what we had now for each object, we have this nerve-based decoder, and you are using this supervising using the patch-based L2 and perception loss. And you do this through generating a feature renderer, and you are generating the patch for each particular person in there. And then you have different losses. So one is the L2 loss, the other one is the one on the feature space, on the VGG space. And you have, again, the two things. So one is the action network, the other one is the dynamic network, and you are generating how the states T and T plus 1 will end up into the generated states, T plus 1. Well, some details, these are the different losses that we have, and we can also understand the learning of the actions, very similar to what we had before. So now what you can obtain, this is something like which you can play it as before. So now you can see that we are, you can manipulate both users. We are not modeling yet the interaction between them in the sense that, of course, this is a causal effect. I mean, if one guy goes to the net, the other guy will do a particular interaction. So here they are all both moved independent, like a Pong game, if you want. But you can also change a little bit the camera. You see, so you are playing around with the camera view, and it's still the game looks reasonable. If you see again, it's all fake because there is no racket, there is no ball. But other way, it looks kind of reasonable. You can also play the field, right? So you can go from one field to, this is the Australian Open, the other one is just on the fake field. And you can have, on one hand, you have pliability. You have multi-objects. They are deformable, of course. You can have camera control. So here is, for example, a kind of a zoom-in type of approach. And you can also change the style. And it's reasonably robust. Yeah, so this is an idea about the learned actions. You can see these are the samples that you can get the distribution of the actions. So they are all, for example, action number 1, the yellow one, they are all part of the action. So the pose will be something like that. If you go into the, let's say, the red action, you see that the pose is completely different. Well, so different limitations. So in our case here, the environment must have fixed geometry. And we assume that the objects are staying on the ground, right? If the guy starts jumping, then we are not able to model it, at least at the moment. And then, well, we are having troubles with seen and fast-moving objects, so that's why, well, we don't have the racket, we don't have the balls, but we are working on it. And we are capturing movement of the object independently, right? So we don't have yet interaction between the object, because there you have some causal effect, and it's far more complex to understand the logic of the game in there. So what we want to do next, and this is something that we are working on it, is to understand the laws of the environment. So we have to see what kind of things you can do there in the game. You have to model some complex spaces. So if you go into some case, let's say the gaming stuff, there the environment is very complex, right? For the tennis game, it's easy, but if you go even to basketball, for example, there are many players. It's a little bit more complex than that. You can also try to get something like, some sort of, get more control of the user. Instead of just having the keyboard to kind of move left and right, you can want something like rush to the right to save the point, or a powerful forehand to the corner, and so on. So if you tell that, then of course the action is a little bit more complex because you understand what's going to happen there. And you can also model other agents, and you can try to model them together as well. Yes? So one idea is to try to use this kind of reinforcement learning agents in the environment to try to see how they move. Because if you move into some particular direction, there could be a penalty or reward that could tell you how would you work on. And then ideally, of course, is to try to model everyday scenes. So one idea that we had is to kind of go, for example, like a traffic scene in which you have pedestrians, you have cars, so you can just model it. That's kind of easy to understand how the laws are done into the game. So we could also have some other type of games. And well, what we don't have yet, and we are working on it, it's again incorporating 3D information. So far there are all some kind of flat models. In many cases it's working fine. For example, you saw also with changing of the head pose. It's kind of reasonable. Of course, if I start to have some very, very strong head poses, it's going to have deformation. But as long as you are kind of in front of the camera, it's working reasonable. We want to model this complex interaction between the actors and the scene. And, well, to have this kind of seamless integration between different modalities, so text, audio, visual information, and so on. And then, well, this is something that we all need to look into. When you do these generation things, of course, you need to look at the privacy and the deepfake detection. This is quite important part.
That's all, folks. Any questions?
So again, this guy that is asking for questions. So, if you have questions, I'll be more than happy to answer. So as you notice, our goal is to go towards complex things and try to give the user, more power, and to try to generate, in my opinion, if you want to go towards video gaming, if you would have video game with real people trying to work. I mean, let's say in soccer, they are doing kind of realistic, but you could have really yourself, or you can put yourself to play with Messi, for example, and you just have yourself and you just run with Messi and you can just pass a ball to Messi and so on. It would be quite cool, right? I mean, just to kind of paste yourself into the real game and play, for example. This is something that we aim at. We are not yet there, but you could kind of put yourself and play tennis with a tennis player right now. But it's working quite reasonable.